Greetings once again. This is the Pinecrest High School AP Physics 1 video series. This is video 8F, Resonance. Resonance refers to two or more systems that vibrate with the same frequency. If that's the case, the systems can share energy, and the amplitude of vibration can get very large very quickly. The best example of resonance, or the most familiar one anyway, is when you push a kid on a swing. The kid on the swing behaves like a simple pendulum. You have the chains or the cables that hold the swing on the bar. The mass is concentrated down at the end. So this simple pendulum has a period and a frequency that depend on the length. You tend to push the kid on the swing more or less at the same point during the cycle. As long as your frequency, the frequency of your push, has the same frequency as the pendulum, the amplitude of the swing's oscillation will increase. It'll get bigger and bigger, which is why you apply the push at the same time as the kid goes past you. If you don't match the frequencies, the amplitude of the oscillation will not increase. So during class we will demonstrate several examples of resonance. We'll have coupled pendulums and tuning fork amplifier boxes and the Tacoma Narrows bridge collapse, which you've probably seen before. There are lots of different examples of resonance that may not jump out at you as being so. Radios are an example of resonance. When you tune the radio to a particular radio station, which is identified by its frequency, the signal is broadcast over electromagnetic radiation that has the frequency that is equal to the call numbers of the station. When you tune a station on your radio, the circuitry in the radio is adjusted such that the current oscillates with the frequency that matches the frequency of the radiation. Then the radio shares energy with the signal, or accepts energy from the signal, and then sends the information to your speakers, which you hear as music. We're also going to watch a video that shows resonance between a pure tone and a crystal wine glass. Ultimately, the wine glass breaks. As long as the tone and the wine glass have the same frequency, the wine glass will vibrate with larger and larger amplitude until it actually breaks. So we will break here for a moment. We'll go to the video, and you can see the glass break under the influence of a pure tone. So you can see the glass is under the influence of a pure tone, and it vibrates with larger and larger frequencies because the tone matches the frequency of the glass itself. So the glass is vibrating, the amplitude gets larger and larger, and eventually the glass can't sustain that amplitude and it blows up. That's a good example of resonance. They show that on Mythbusters also. Alright, now most people have picked up a bottle that's almost empty and blown across the opening in order to produce a tone. This is the principle of tube resonance, in which a column of air vibrates with a characteristic frequency. That is the air inside the bottle. When you exhale, the sound that you produce is a mixture of many frequencies that's called white noise. If the frequency of the volume of air in the bottle is included in that mixture of frequencies, the air column will vibrate. They'll resonate, and the air column will vibrate with larger and larger amplitude, and it will produce the tone. This is what's called closed tube resonance. The tube is open at one end, that's the top of the bottle here, and closed at the other end. There's also open tube resonance, when the tube is open at both ends, kind of like the tubes in a pipe organ. So what we see here are harmonics and overtones in open and closed tube resonance. What you're looking at here, represented as transverse waves, are really air displacement antinodes. We know that sound is a longitudinal pressure wave, so it would be probably more accurate to show these as compressions and rarefactions, but probably not as clear in terms of the reflection and the antinodes at the openings of the tube. The harmonics here are similar to those in a string, although in the closed tube the harmonics don't include the even numbered harmonics because of the relationship between the wavelength and the length of the tube. So the important thing, the mathematical relationship that is important here, is that the tube length, in order to create resonance, the tube length has to be for the wavelength of sound that resonates in the tube divided by 4. And that's a consequence of having to have that antinode at the opening. The wave goes into the tube, reflects off the back end, and comes out again with an antinode at the same location at the opening of the tube. So we're going to show this in class also with a device called a sonometer. The sonometer has a column of water here and a tube that connects it to this reservoir. You can move the reservoir up and down, and that'll change the water level in the tube so that you can effectively change the height of the air column above the tube. And what we'll do, this is effectively a closed tube. It's closed at the back end where the water is and open at the top. We use this relationship here that the wavelength is 4 times the height of the column, along with the speed of sound, which is equal to f times lambda. We can match the height of the column to a given frequency, and then we can make the tuning fork with the frequency that matches resonate with the tube, just like the boxes do on the bottoms of those tuning forks with the resonator boxes on them. Okay, so that's it for resonance. Next up is Doppler Effect, and then that'll do it for waves and sound. Until then, enjoy, and I'll see you again next time.